Okay, everybody, this kind of follows up then on from the last video on horsepower. What we're looking at now is flow rate and what happens when we have maybe an input or a prime mover to our pump, which is much greater horsepower than what we actually do, or where we're creating a whole lot more flow than we actually need. All right, so as the title indicates here, pump flow determines speed. That is a main thing to remember when we're looking at any hydraulic system. The amount of flow coming out of the pump will determine how fast any of the actuators can actually work. We know that all the time, right? If you're running a piece of equipment and you want the piece of equipment to work faster, whether it's a loader lifting or a motor turning, you simply increase the speed of the flow to it by either revving up the engine or opening the valve so more flow can occur, and we get more speed. All right, but here's kind of and again, it's in your handout, so you look at it. We have our pump creating flow, and we're working against a piston or an actuator, and we're getting some work done. All right, so the pump is pushing out 10 gallons per minute. All right, we're going to move 10 gallons into the piston. So it makes logical sense then that, I mean, it's a huge piston, but if at 10 gallons per minute, it's going to take 1 minute for that piston to fully extend. The fluid will be just returned back to the reservoir, and we have a very simple hydraulic circuit. All right? To reduce the speed or reduce the flow, what we can do is either through a directional control valve or pressure control valve, we divert some of the flow to back to the reservoir without doing any work. All right? So in the case of this, we have 10 gallons per minute coming out, and we're only allowing 5 gallons by use of a flow control valve at this point. So if the pump's putting out 10 and we're only using 5, that oil has to have a return path back to the reservoir. And it makes sense that now half my flow is going this way, it's going to take twice as long for my piston to fill and twice as long to extend. All right? Now, this one, we change the numbers up a little bit. We have, we'll just go over the outline very quickly. We have a pump operated by an electric motor, which creates flow and fills my piston. We do some work with the piston rod, and we return the fluid back to the reservoir. My pressure regulator is set at 2,000 psi. All right, and we're set here, and you can see that's what I'm reading on my gauge, and we're getting 20 gallons per minute is my flow rate. Remember when we did the horsepower calculations, I literally have all the information now to calculate how much input I need on this prime mover. So 20 gallons times 2,000 psi divided by the 1714, 17,000 or 1,714 equals 23.3 horsepower. That is what it's going to take to maintain that hydraulic system. All right, now, each of these pictures gets a little bit more advanced. We maintain the 20 gallons per minute. We maintain the 2,000 psi. But now we put a variable flow restriction onto this, and we're only going to, of the 20 gallons we're putting out, we are only going to use 5 gallons to move the piston out against the load. The other 15 gallons that the pump created flow, though, must be returned. So we return 15 gallons directly back to here. And we're really only using 5.8 horsepower to actually do any real work. All right? So, you know, it comes into what happens when we're putting way more into the oil than we're actually using that hydraulics to do any real work. Well, the laws for mechanical efficiency and thermodynamics have to apply. We cannot create or destroy energy, but we can transfer it from one form to another. And so in this case, we're putting 23.8 horsepower. I can't see, the numbers are too small. 23.8 horsepower into here, which means that some of that work is being done to the oil, and it's actually will warm it up. So we're converting one form of energy into another. All right. From the next slide, then we can do, so we look at it and we're basically going, wasted energy is 17.5 horsepower, all right, which is basically going to mean that when we've got this, remember that the diamond sign means that it's something that conditions the fluid, and in this case, because I have two arrows that are pointing out, it is the heat exchanger. So I have to get rid of 17.5 horsepower of energy back out to the air, because now I've converted it to heat, and I got to get rid of it, or if I don't, the temperature of the oil will just continue to rise, and then we'll boil the oil and it won't be very good. All right, so it kind of, that's why I'm going back to the other video where I said, you know, we look at how much horsepower it's going to take to drive the pump, and then try and have an input motor, a prime mover that matches that design. We wouldn't take a 350 small block Chevy and put it on a wood splitter to operate it, because it would be wasteful. We would burn way more fuel than we would need to actually do that. If you think about it, like, you know, you see a little Briggs & Stratton or something on there, excuse me, it does the job fine. So you match your input, your prime mover, for what you need to get the work done. All right, that's that one.